At Northrop Grumman, innovation isn't just an idea. It's a way of life. The value of performance. Northrop Grumman.
Thanks so much. It's always a pleasure to speak at this festival, especially this year to follow Paul. Super talk. And of course, you guys know how important it is to get away from the toxic substances and go towards green chemistry. But the fact is that in chemistry, we do have a problem. Whenever I talk to groups and mention that I'm a chemist, there are various opinions that are almost immediately evoked. First of all, there's usually fear. People are worried about chemistry. And if they're not worried, they think, boy, are they ever going to listen to a boring discussion? Because many of the memories from school about chemistry are not all that great. And then there are those who think that we're nerds and that, you know, we're just kind of different from everyone else. And then, of course, there's the image of the mad scientist. And that is particularly a troublesome one, because people believe that we chemists are somehow locked up in laboratories just waiting to unleash some cancer-causing additive on the unsuspecting public. And of course, the overall opinion is that chemists are a different breed from everyone else. Well, this, of course, is not so. But there certainly is a lot of concern. The word chemical has become virtually synonymous with toxin or with poison. You go into the bookstore and you see numerous books like this about toxic substances in the environment. And of course, it is important to point out that we have concerns about many of the substances that we've become accustomed to using. But it is also possible to go out and get people to sign a petition to ban dihydrogen monoxide by telling them that it's found in cancer cells, that you can use it to wash garage floors, and that it gets into our bodies. Well, of course, dihydrogen monoxide is nothing more than just good old H2O or water. But it is scary that you can go out and get people to sign a petition to ban dihydrogen monoxide. And that is reflective of the scientific illiteracy that is out there, the lack of knowledge about how science works and what chemicals really are all about. And I think one of the most frightening aspects of this is that you can go and purchase a chemistry set these days, the advertisement being that you can perform these activities with no chemicals required. Imagine that, buying a chemistry set that contains no chemicals, which of course conjures up images that everything about chemicals are worrisome and dangerous, and that chemistry is really the work of the devil. Well, my view is that chemistry really should be in the limelight, because it is the science that ties all the others together. It is the thread that fuses all of the other sciences, both literally and figuratively, because of course our fabrics, our threads, obviously are composed of chemicals. But chemistry is defined as the study of matter and the changes that matter undergoes, which really means everything, because matter is everything that occupies space and has any sort of mass to it. So chemistry encompasses absolutely everything. It is the root of biology. It is the root of biochemistry, of engineering. Everything is somehow based upon chemicals. And they are not to be feared, and of course, neither are they to be worshipped. They are to be understood. It is ignorance that breeds fear. And once we have an understanding, we know the kind of decisions we can make about chemicals, because they are everywhere. They're under our sink, the cleaning agents. They're in our medicine cabinet in the bathroom, which is, of course, the worst place to keep your medicines because it's a hot, humid environment, and it will degrade the chemicals. We call them drugs, but of course they are just chemicals. And of course, when we go outside in nature, look at the beauty of nature. What are we seeing? All of those colors, those are just different molecules. They're anthocyanins mostly that make up everything that we see there. And of course, the food that we eat is nothing more than a collage of chemicals, and we grow it by using fertilizer, which of course is just another aspect of chemistry. And then we go and cook our food. Well, what are we really doing when we're cooking? We are rearranging molecules. That's what we do. Cooking is chemistry in action. And then we wrap that food in various kind of chemicals in order to preserve it. But of course, issues arise here too, because what happens to all of that wrapping? What happens to those styrofoam containers? Unfortunately, a lot of the time they just get thrown into the garbage and they get into landfills. That's not the way things should be happening, because those plastics can become your park benches. They can become the clothes that you wear through clever recycling. We know the chemistry needed. We know the technology. We can make it happen. It takes willpower. Believe it or not, 25% of all of the bottles that you drink from, the water bottles, the juice bottles made of polyester, only 25% of those globally get recycled. 75% end up in landfills. That's a waste. This can be readily recycled. Don't ever throw out one of those bottles, but yet people do. Even our own waste, of course, is nothing more than a collage of chemicals. Believe it or not, there are chemists who work on that, and we know that there are over 200 different compounds that can be isolated from human waste. We're not quite at the recycling point there, although composting, of course, is a type of recycling. So the message is that chemicals are absolutely everywhere, and we make decisions based on chemistry. Numerous times during the day, we come to the proverbial fork in the road in our mind. We have to make decisions. You get up in the morning, are you going to have tea or coffee? And if coffee, what kind? Caffeinated or decaffeinated? If decaffeinated, how? By the carbon dioxide process or by the dry cleaning method? You're going to have lunch. Is it going to be pizza, or is it going to be cheese or smoked meat or whatever? Those are chemical decisions. You cook at night. You decide if it is going to be in copper, in stainless steel, or aluminum. People worry about aluminum because they've heard connections between aluminum and Alzheimer's disease. I've been cooking in aluminum all my life, and I don't remember any problems. So we make decisions all the time, and they are based upon chemicals. That's why we need to have knowledge of how all of this works. But this is the image that people have of chemicals. That chemists go around burning things, exploding things. Well, I don't want to really disappoint you, because you come to this little chemistry performance and you expect to see something, right? And burn or explode. And so, I mean, we do light up things in chemistry. I mean, that's a chemical reaction right here. We have a fuel that's burning. But this is, I think, more interesting. Well, you saw something there that looks kind of nifty, and I like to do that, but I don't like to do it without an explanation and without telling you what the story behind it is, because that's where the beauty of chemistry comes to the fore. It's in the story. So let's go back to the middle 1800s and a Swiss chemist by the name of Friedrich Schönbein, who, at least according to the legend, used to take his work home with him. And his work involved nitric acid and sulfuric acid. And one day he happened to spill it in his kitchen. Luckily, Frau Schönbein wasn't home at the time, so he decided he better mop up this mess. But with what? His wife's cotton apron was hanging on the wall, so he quickly grabbed it and wiped up the mess on the floor. And then he had a wet apron on his hand. What to do with that wet apron? So he took the wet apron and he hung it up in front of the fireplace to dry. And the next thing he saw was that. The apron vanished in front of his eyes. He knew he had made a discovery. He just didn't know what it was. The world wasn't waiting for vanishing aprons, but the world was waiting for something else, smokeless gunpowder. Because in those days, gunpowder was made the old-fashioned way, with charcoal, sulfur, and saltpeter. And a cloud of smoke hung over an army when weapons were fired, so the enemy knew exactly where they were. And Schönbein now noticed that his apron had burned without any smoke. He knew that it was made of cellulose, being a chemist, cotton is cellulose, and he figured it must have reacted with the acids. Indeed, he had accidentally discovered cellulose nitrate, or gun cotton as it came to be called. And within a very short time, he found a way to grind it up into a powder, and thus was born smokeless gunpowder. Now, you might think that it is bizarre to talk about chemistry and use gunpowder as an invention, as something positive. Well, it all depends on how you look at it, isn't it? Because gunpowder can be used to blow up buildings by terrorists, or it can be used to allow the building of tunnels through mountains. That gunpowder doesn't make that decision. We make that decision. So the chemicals are not good or bad. They don't make the decision. We, as humans, make the decision. And Schoenbein made an interesting discovery. He looked at something that others would have looked at, but he came to a conclusion that others probably would not. And that's what invention is all about, is seeing what everyone else sees and thinking what no one else thinks. That's really the beauty of science. So there are no safe substances, only safe ways to use substances. And that, of course, is what we are always after in chemistry, how to do things the safest way. Well, I got interested in this at an age very much like you heard from Paul. I was actually in grade 6, and I was invited to a birthday party. And that's where the chemistry and the magic happened for me. Because there was an entertainer there. He was a teenager, but to us he looked like an accomplished pro. He wasn't very good. Most of the tricks he did were eminently forgettable. But he captured my imagination. You know how? Because he took out a rope, and he said, "Have you guys ever seen a rope hypnotized?" So of course, we didn't even know what hypnosis was all about. And then he proceeded to show us. He said, "Look, you can take a rope and take a magic chemical," and he reached into his pocket, took out a magic chemical that he sprinkled on the rope, and believe it or not, the rope was hypnotized. Now, we knew that if a scientist tried to do that, this is what would happen. But a magician was able to do it. Now, I knew it wasn't anything to do with any sort of magic chemical. But I didn't know how he had done it, but I went to the school library and took out a book on magic and took out a book on chemistry. And I followed both of those ever since. And you might think that that's a bizarre juxtaposition, magic and chemistry. It isn't really. Why? Because a magician is an actor on the stage playing the role of a magician. Everything he or she does is done by perfectly explicable scientific means. It's just that the audience isn't privy to that. In chemistry, of course, we relish in giving out the explanation, but until you know the explanation, it's pretty magical. Let me give you an example. What do I have here? Water? How do you know? I just poured it? How do you know what I poured? What's the scientific answer? A liquid, a clear liquid. That is the only thing you can say based on the observation that you've made. It could be nitric acid. It could be vinegar. It could be a bunch of things. Happens to be water. I have a coffee cup here. I propose to pour this water into this coffee cup. Let me do that. Did it go in there? It did not go up my sleeve, correct? That would be a lot better trick. No, it went in there. Well, then how come I can do this? Oh, I know you're thinking, yeah, of course, I studied some physics and do it fast enough, the centrifugal force keeps the water in there. But I told you I'm a chemist, we're better than physicists. Let's see if physicists do that. Well, it seems that the water has vanished. But matter cannot be created, it cannot be destroyed, it can only be changed from one form to the other. It still is in there. It's just that it is in a different form. Right? I showed you I had a coffee cup. I suggested it was empty. I never said it was. Because in the bottom, we had a substance called sodium polyacrylate. We affectionately call it super slurper. It has a fantastic ability of absorbing water. This is the magic behind super-absorbent diapers. That's what keeps the wee-wee away from the baby's bottom. So now you have an explanation. Now the magic is gone. Science has appeared in its place. This is what got me going, both the magic and the chemistry. And it was followed by my infatuation with a young lady who starred in a TV show called Dream of Jeannie. I liked that show. I especially wondered about how they made her come out with that smoke. And I didn't find that out until I was in graduate school in chemistry. I hoped that I would grow up and get to know her better, because Barbara Eden was kind of a charming lady. But that never happened. But I did get to find out how they made that smoke come out of the bottle. It's a simple chemical reaction. You take hydrogen peroxide, add a catalyst called manganese dioxide, and you get water at a very high temperature, changes into water vapor, it condenses into liquid water, that's a cloud, that's the smoke. In the container, they had two parts. One had the manganese dioxide, the other one had the hydrogen peroxide. When her master, played by Larry Hagman, very good, picked up the bottle and twisted it, the two chemicals mixed together and out came the smoke. So I thought that was great, and it gave me the idea for one of my books about the genie in the bottle, because it enabled me to tell this story. Plus, furthermore, I thought that the genie in the bottle was a wonderful metaphor for chemistry, because that's what it is. It can do wonderful things, but boy, once that genie is out of the bottle, you're not going to get it back in. So we better know how to use those chemicals properly. But chemistry is indeed a very, very colorful topic, isn't it? Not everybody thinks that that is the case. I mean, to so many, chemistry is kind of a dark science, right? Well, not to me. To me, it is colorful because everything here that you see is a different chemical. That's what colors are. And therein lies a fascinating story. Think of Joseph's coat of many colors thousands of years ago. How could they have done that? There was no chemical industry. If you wanted red, you better have known where to find a madder bush, because the roots of the madder plant give you a red color. If you wanted blue, you needed indigo. We still use indigo today. Your genes are colored with indigo, no longer extracted from the plant. Today, it can be made synthetically. Today, we have virtually every color of the rainbow available to us. Not problem-free, as you heard, because some of those dyes do come at an expense to the environment. But there certainly are natural dyes that can be used as well. They sometimes have to be chemically manipulated to make them effective, but that's where our science comes in. Dyes are fascinating to anyone who practices chemistry, because you look at the world and it is so colorful. Everywhere you look, there are different colors. But it all started with one specific color, that is the synthetic dye industry. It started with the color mauve. And therein lies one of the most fascinating of all chemical tales. Again, we go back to the 1800s, the era of Queen Victoria and her husband, Prince Albert. Prince Albert was of German origin, and in those days, Germany was at the forefront of scientific research and technology. And Prince Albert wanted England to catch up because he thought that England was behind in terms of chemistry. So he invited Professor August Wilhelm Hofmann to come to London in England to set up the first ever College of Chemistry. It was the Royal College. It was for mature, experienced students. But one day there was a knock on the door from a young 16-year-old by the name of William Henry Perkin, who had fallen in love with chemistry at a very young age, very unusual, because there was no formal chemical education, certainly not in elementary school in those days, but he did some reading by himself, he did some experiments, and he thought this was the career that he wanted, but he was too young. But he knocked on the door and he said he would do anything. He would wash dishes, he would help the other students. And he must have been a persistent little critter because Hoffman said okay, and he let him in. And he turned out to be very good in terms of helping the other students. And then the Easter holidays rolled around, and the college was going to be shut down for 2 weeks. He didn't want to be without chemistry for 2 weeks. I'm sure you can appreciate that. Nobody would. So he asked Hoffman, what can I do? And he said, go and relax. But he was very annoying and persistent. Hoffman finally said, go and try to make some quinine. Quinine was much needed in those days to battle malaria. And it was extracted from the bark of a tree that grew in South America called the cinchona tree. Very difficult to get. There wasn't enough of it in Europe. But Hoffman had done some interesting experiments and found the empirical formula for the powder that was extracted from the tree that cured malaria. They didn't know anything about molecular structure, but they were able to do chemical analyses. And it occurred to him that this analysis yielded a formula that was very similar to a compound that he had isolated from coal tar. After coal burns, it leaves a tar behind. And he had isolated a substance called aniline, which was very similar in chemical composition, but it was missing some oxygen. So he said to young Perkin, go and use an oxidizing agent. See if you can implant some oxygen into that aniline and make quinine. In retrospect, we know that this was pie in the sky. It was impossible. Quinine is a very complex molecule. There was no way of synthesizing it, but at the time, it seemed like a reasonable approach. So Perkin went home, and he built a laboratory, and he began to add various oxidizing agents to aniline. Nothing worked. One day, he came up with a gum. He couldn't clean out his flask. He tried soap and water, it didn't work. He finally resorted to alcohol. He poured in some alcohol, and all of a sudden, the sink turned into a beautiful color, a color he had never seen before, a color that eventually came to be called mauve. He recognized he had made a discovery. Others would have looked at the sink and said, gee, how do I clean that? But he knew he had made a synthetic dye. Luckily, his father had money. He borrowed some, and he built a little factory at Greenford Green in London, and the dye industry was born. Not only did he synthesize mauve, which the Queen loved, but he was able to make a variety of other colors, and if the Queen wore mauve, everyone wanted it. In fact, the decade after its discovery is still known today as the Mauve Decade. If any of you collect stamps, the penny royals from the 1860s were colored with mauve. It was the beginning of the dye industry. Perkin became the grand old man of chemistry. He actually retired from business in his 30s. He became so rich, but he dedicated the rest of his life to doing chemistry. And those of you who will go on to study some organic chemistry will learn about the Perkin reaction. All goes back to him. In 1906, he was invited to come to New York to be the recipient of the first ever Perkin Medal. And what an event that was. It was held at a restaurant called Delmonico's in New York, which is still there today. And in fact, the Perkin Medal is given out every year to a top chemist in North America. It's one of the most sought-after awards. And the dinner is spectacular. Here's the original dinner with Perkin, and you see everyone is wearing a bow tie. Those bow ties were all colored with mauve. And so it is to this day, because when he came in 1906, he left a vial of his original mauve at Columbia University. And every year they take out a bit of that and they color some silk. And if you get lucky enough to be invited to the Perkin dinner, with the invitation, you get a mauve bow tie, which of course represents the beginning of the chemical industry. But not only the dye industry, because if you could make synthetic dyes, you could make any kind of other substances synthetically as well. So it wasn't long before Paul Ehrlich in Germany realized that you could do with drugs what Perkin had done with dyes. You could make them from substances extracted from coal tar, and thus was born salvarsan, the first antibiotic. And then discoveries came quicker. Nylon in 1939 was introduced. Nylon is a magical fabric, and we use nylon ropes all over the place. If you ever go boating, sailing, the ropes that you use are nylon. And boy, does it ever work in a magical way. Right? Well, that takes a little bit more than just making the nylon. But nylon is indeed a fantastic material. Women couldn't wait to try on their nylon stockings. 1941 was Nylon Day at Macy's in New York. And nylon made a big contribution to the war effort as well, because the US was cut off from the silk supplies in the Orient by the Japanese, and silk was needed for parachutes. Now they had nylon, and you don't win a war without parachutes. The war also needed nourishment, and soldiers were given chocolates in their battle rations. Another interesting chemical concoction, but the trouble was, often they would wage war in warm areas, and the chocolate would melt. So Hershey's came up with the tropical chocolate. They chemically modified it so that it wouldn't melt. It wasn't very tasty. So the word went out from the US Army, they wanted someone to find a way to make chocolates melt in the mouth and not in the hand, because soldiers would quickly grab their rifles, and if their fingers were chocolatey, it would slide off the trigger. And as you guessed it, thus were born M&Ms. Mars and Murray Company, Alfred Stern at the New Jersey Company found a way to take chocolate, cool it down, and then coat it with a candy. And he thought that, gee, this would be great. It wouldn't melt, but there was a problem. He didn't know his physics, because the chocolate and candy coating didn't expand at the same rate. So the candy coating cracked, but he went back into the laboratory and he found a solution. When he was cooling the chocolate, he blew air into it, and that made little pockets. So now when the chocolate expanded, it expanded into those little air pockets. And you can check this out. You can do an autopsy. You can take an M&M, bite it in half, and take a look at the little bubbles that helped defeat Hitler. And after the war, everybody wanted chocolates. We still love them. They're the classic gift of lovers, right? On Valentine's Day, that's what happens. And here too, finally, there is some chemistry that people like to put into action. Because there's a chemical in chocolate called phenylethylamine, the same chemical that is found in the brains of lovers. How do we know this? Lovers don't sacrifice their brain, of course, for science. But there's a metabolite of phenylethylamine called phenylacetic acid that comes out in the urine. So to put it bluntly, people in love pee differently from people who are not. So it makes a great story on Valentine's Day, but the truth is that the phenylethylamine in the chocolate never gets to the brain. It goes directly to the hips, right? But it's kind of an alluring story. So, as you can see, chemical investigation is neat. It is worthwhile. You never know what you're going to find. Curiosity is really the spark of science. Although, sometimes people say curiosity kills the cat. Well, only if the cat is looking into that toilet bowl where someone has mixed an acid and Javex, because then it will be overcome by chlorine, and that's highly toxic. So no, you don't want to do that. That's why we need to know the chemistry. It really is the Dr. Jekyll and Mr. Hyde science. We can do wonderful things, but we need to know how to use it properly. So let's not throw out the baby with the bathwater. Let's make sure that we use chemistry properly. We don't need to lock away all chemicals, because there is, in fact, beauty and functionality in chemistry. But I want to leave you with one last idea to satisfy your curiosity. No, I'm not a mad scientist. We need to get rid of that notion totally. But what we need to do is remember that education is all about creativity. So I want to leave you with this last example. I have this bizarre thing here. It has straight edges and hinges. How many different shapes can you make out of this? Triangle, in fact, 2 triangles, pentagon, parallelogram, square, of course. Can you make a circle? No. The answer, how can you make a circle if you have straight edges and hinges? But of course, in science, if you think about it properly, and sometimes you have to think in a different dimension, you can make a circle out of a square. And that is what you guys need to do. You need to go out there and look at the same things that everyone looks at and think what nobody has thought before. Good luck, and I'm sure some of you sitting in this room will be able to take that square and make a circle out of it.